Okay, guys. Um, Welcome to lecture 3 of the reinforcement learning mini course. We're almost done. After this, it's only one more. So today we're going to go into model-free learning. Um, yeah. So last time I talked about the Markov decision process, right? And I, talked about what trajectories were and have like an episodic task, things that end. Or not necessarily, maybe they're continuous, and introduced dynamic programming, which we found out by the end isn't really that useful to implement, but it lays down a lot of the groundwork for us. It introduced the Bellman backup um, and how we can um, improve a policy, right? We start with a random policy, how we can improve uh, under this context. So today, we're going to go into model-free learning. So in dynamic programming, you saw that we depended on you having a description of the environment of the world in terms of some sort of transition matrix, right? It, it tells you the probability of making a transition from one state to another. And that's one of the limitations of dynamic programming. So today we say, okay, let's do, I'm going to talk about Monte Carlo indifference learning, and where you don't have a model. You're just going to let the environment respond to you, respond to your actions, and it'll tell you what the new state is. So you don't know what's under the hood. And I alluded to it last time. In these, the states, the state space that we're considering is all discrete. There's only like a finite number of states you could jump to. So what happens when your state is some continuous variable, right? So I'm going to end today with artificial neural networks as a way to treat continuous state spaces. And I think with that, we will have, I've pretty much run you through the whole gamut of this RL introduction to now where we can tackle real world problems. And so next time, I'm going to put it all together and we're going to dive into some code, hopefully. Hopefully we'll code, in real time, but probably not. Put all together and tack on an agent onto that snake game I coded up for you guys to make the snake, well, get high scores, possibly be even better than a human. Who knows? Okay, so let's move on. I'll just, this one again is the same boilerplate one. So here's the GitHub repo for us, and for coding, I basically just use Atom. This is going to become more important next lecture. Today, it's pretty much theory. All right, so recapping the big RL framework, right? We have an environment that exists at a current state, and we have an agent that reads that state, the current state of the environment, and based on that, it'll make an action, right? That action, the environment is then going to respond to that action and update its state, change to new state, and also have some value, some reward associated with that action, right? Like how good was that action you took, and pass those along to the agent again, and to propagate this episode iteratively like this, right? So each one of these cycles through it is one of these increments in this episode. This is what we talked about last time. Okay. So I told you guys about policy improvement under dynamic programming, right? Where what we do is you have a policy, pi, and you say, let's instead not follow the policy that I know, but follow the action that maximizes that rewards the sum of future rewards, and use that to update a new policy so that I'm sort of improving my estimate of what the policy is, right? So the example I gave was this grid world, right? So in the beginning, you assign all of the states, some default initial value. Here they're all zero since you don't know one state is particularly better than another, right? Um, remember last time these gray squares are the end states. That's where you want to get to, and the policy set. Sorry, and the rewards are actually negative. Every time you move from one state to another, it costs you 1 point. And the point and the goal here is to get to the end as quickly as possible because it's going to cost you the least amount of points, right? So in the beginning, all states are equally valued. And then, so here's that policy. This is the policy that it's that's judging the value of the action, the value of the action for the given state. So for example, in this state, going up has just as much value as going down, going left or going right, going left or right. Right? Because all these new states have, you know, they're equally valued. So all actions are there's no max, right, in each one of these. So if you were to use this policy now and generate episodes, right? In this case, they'd be random episodes, right? You start in this state, it's random. Go to this state, go to this state. No state is preferable, and eventually you'll reach the end. That one episode you use to calculate the new estimates, the values for each state using the sum of discounted future rewards, you know, so how long did it take you to get to the end? And you could assign values to these. So these end states have a value of 0 because it didn't cost anything. You didn't have to move at all to get to the end state. This is on average, right? So making a move from here on average is going to cost you -1 point because why? Because all moving to any state was equally probable. But now notice that the values are different from your initial ones, and so that dictates a new policy, right? So this state, for example, there's a clear winner. This state has a higher value than any of its neighbors, so the policy says to pick the best move, and that's going to be this one. So for this state, the best move is that. For this state, the best move is this, right? And for all the others, it's equally likely. So this is the new policy, and you use it to generate new trajectories, and you get new estimates for the state values, so on and so forth until you reach an optimal policy. So this is kind of like the you know the old hat we're going to be playing all the time here, right? So the update is going to involve the max action, the action that maximizes this value, this number here, which is the estimate of your sum of future rewards. Okay. So I kind of basically just said it in words how the value iteration worked last time. Last time I explained that you didn't have to run the episodes to convergence. You could just do it step by step, and we came up with this efficient approximate method to solve for the optimal policy that basically says generate start from a state, you know, and then pick the max value, the action that maximizes this value, just like before, and just use it immediately to update the state. And you immediately to update the value of that state. Do this until the difference between your old value and your new updated value is below some threshold, and then stop. And so that's a rather efficient way to go about it. So this is how we're going to do value iteration. The problem with this method, or one of the hangups, is this term right here, right? This is the probability of ending up in state S prime, starting in state S, and taking action A, right? You need a model of the environment that'll tell you what this probability is, right? What if you don't know that? What if you don't know that? Well, this is where Monte Carlo comes in. It says, okay, let's just have the environment be its own black box and let it decide what the next state is. And then you can calculate these probabilities by experience, right? You start in one state, take an action, and let the environment tell you what the new state and reward are. do this a bunch of times, a bunch of different episodes, and you're going to build up your own statistics that you can use then to update. So this is how Monte Carlo is going to work, right? So this is our first introduction to like a model-free estimator. So here, what we want to do is we want to estimate the value at each state. So what you do is you just initialize it, this value vector for all the states, initialize it arbitrarily, 0, like we had before. Or every state is valued 0, right? And you're going to keep a tally, right? You're going to keep a record of all the returns you get, right? Because you need this history to build your statistics, right? So right now, the returns for all the states is just an empty list, right? So every state has some returns on it. Right now, it's just empty. Okay, so now we just loop forever. And what we're going to do is we're going to generate an entire episode, right? You're following that policy. So you start in a state as 0, you take action A0, it gives you a return at the next state, and the environment has updated the state, and then you use that, you use your current estimate of your policy, right? That's just going to be take the action with the highest value, and that's going to give you the next, so that's the action, and it gives you the next state, reward, so on and so forth until the episode ends, right? So you've generated an episode, right? You initialize G. G is going to be, remember, this is your sum of future rewards, right? Right now it's 0. We don't know what it is, but we're going to now loop over each step in that episode, okay? And we're going to say G. We're going to update G. G is going to be, for each step, take the reward that you realized for taking from this state and action, you realized the reward, take that and add to it some discounted sum of future rewards, right? And this is just your current estimate. So G is 0, so the first term is 0. The next term, on the next iteration, it's going to have the RT term in it, and it's going to be discounted by gamma. And you add on the new RT term, and you can see how as you march along the trajectory, the episode, we're discounting the sum of the rewards realized in states further back in time. Right? Okay, so this is how you update your sum of future rewards, right? And then what you do is you keep a tally of how many times a particular state was visited, right? And if it's the first time you visit that state, then you can append G to the returns of S, so to this list of returns. So in other words, the return for any state is going to be the sum of future rewards only when you when you visit that state for the first time, right? If you visit it a second time, that doesn't count to its rewards because presumably that would be a future reward, right? You visited that state in the future. So that this is the important step here is that from your trajectory, you march along the time, and if it's the first time you encountered that state, then go ahead and update this list of rewards for that state. So each state's only going to have one value, right? And then now you can update your value estimate. For that state is going to be the average of that list of returns for that one state. So this is how you do the Monte Carlo estimate for the value on each state. Okay, so the important things here are that first visit criteria here. You only add to this list when it's the first state, not when you return to that state again. And the other thing is that you actually need the task needs to be episodic. It needs to end. if it went on forever, you couldn't, you wouldn't know when to stop, because who knows if you're going to encounter a brand new state that you've never seen before in the future, right? So that's the other caveat, that this only works for episodic tasks that will end. The other thing is that you can't, you need to generate an entire episode before you can begin this calculation, right? So in this loop, you say, okay, let's start a new episode. So you engage the environment, right? You start in S0. Well, the environment starts up and it says I'm in state S0, and then you say, based on my value estimate for each state, for that state, I'm going to take this action. And then the environment responds with the new state and new reward, and then you give it the next action, and so on and so forth. And you have to engage the environment for an entire episode before you can do this estimate, where you loop over the steps in that entire episode, right? So that has to be all held in memory. And if this is really long, then maybe that's not that great. Oh yeah, and this can be huge. Like this, if the state space is huge, then that just makes this task uh, even more expensive. Okay. Any questions so far? This is a kind of like our first step into like model free estimate.
Yeah.
Yeah. So if anything to remember here is that you need to generate an entire. You can't begin your estimate until you generate an entire episode, and that could be long. Okay. So what about control, right? So now to do control, you have to have a way to calculate the value for each state, right? Just like we did before with dynamic programming. So now that we know how to calculate the value for each state, maybe it's expensive, but at least you can do it. Now we can say, use that value to update your current policy, right? Just like we did before, right? So you start with a policy, that's this estimate here gives you values. These Q values are these. And then those Q values will determine what the best policy is, right? What's the best action, and then use that best action to update the values, and then use those values to update the policy, just like before, right? So again, you're going to choose the action for each state. The policy is going to be that you choose the action that maximizes this value, right? This is the value assigned to that state given that you take that action, just like we did before here. Okay, so how do we do it with Monte Carlo? Well, just like before, we assign a policy. This is going to be what action to take at a given state arbitrarily, right? Maybe for all states in the beginning, the policy is random, right? It could be equally likely for anyone. Now you assign this is the Q value. This assigns a value to that state, given that you took that action, right? And this is going to be basically how many future rewards can I expect when I'm in this state, when this combination of this state, and if I'm at this state and I take this action, what can I expect my rewards to be, right? So we initialize that all to 0 because we don't know anything. And we need to keep a tally of our returns realized at every state action pair, right? That we are going to visit in some sort of episode. And right now it's an empty list. Okay, so just like before, we're going to loop forever. We get a new episode, right? And we say, okay, we're going to choose the initial state and action randomly, right? And I need to randomly, and they all have the same probability. Well, they all have some probability, right? You do this so that you sample the state space, right? So you can think of it this way: if I always started from the same spot, then maybe I'm not looking at the resulting episodes will one be all correlated, but two may not sample. You may not explore the regions of state space at all if you start in a certain spot. Maybe there's a big energy barrier between two regions of the state space that it's really hard to cross over. If you started in one, you're going to stay in one side of the state space, and if you start another, you start another, and you stay in that other. So what you need to do is you need to sample the distribution of the state space, right? So that's what this is doing. So you sample, and that could be hard, right? If the state space is huge, it may be almost impossible to sample that state space well. But so now that you have the initial condition, you can generate an episode, right? By engaging the environment. Say, okay, I started in this state and I chose to take this action. And the environment says, oh, okay, so your reward for that is R1 and the new state is S1 and da 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 da. And eventually the episode concludes, right? And now you do it again. You do this estimate for the sum of future rewards for each one of those states. You initialize it to 0. You're going to march along each step in that episode, and you're going to update that value of G, that sum, right? The discounted sum of rewards. You're going to update it, and and then again, right? If that pair ST appears in your trajectory, then you append it. You append that reward. I got a reward, reward G, when I encountered the state action pair, right? You add it to the list. And then my Q estimate, the value for that state action pair, right? When I was in this state and I took this action, the value I have is going to be the average of all those returns I got that I've logged in this list here, right? And so finally, my policy then is just going to be the action that maximizes this value. The policy at this state is going to be the action that maximizes this value. Okay, so it's subtly different from what the algorithm I showed before. Basically, it means that you have to sample the initial condition, the starting state, well. And like I said, that might be hard, right? Also, notice right here when we're updating, like you need to be in this exact state action pair state, right? This state, I took this action. I could have taken a different action, but I could have taken a different action, but I took this specific one. So this specific state action pair, it may not appear in the trajectory, right? Or maybe it's like really rare, right? But only then will you update. So this can be sparse, right? If the number of states is big and the number of actions is big too, then the chances of you hitting a specific state action pair in any given trajectory might be low. So this may update really slow. And maybe there are even some state action pairs that never get updated because you never visit them. Despite starting in, even if you were to sample well the starting conditions, maybe, along those trajectories, still some states get sampled so infrequently. So that's the other limitation to doing Monte Carlo control in this fashion. But when the state space is small, when you have like 10 states and maybe 2 actions to take at each state, then you could probably brute force it like this to get a good policy. Okay. Any questions so far? I haven't given any pictures. This is all just like pseudocode. Yeah. So all we're doing here is solving for the policy at a given state. Okay. So 2 lectures ago now, I introduced the idea of exploration versus exploitation, right? And one of the ways we can improve the previous algorithm is to, I'm just gonna back up here, is to not take the best action every time, but rather take the best action with a certain probability and with a certain probability 1 minus epsilon, and then at some with and with probability epsilon take some random action, so that you're always exploring. That way you can go off policy, right? And by going off policy, you stand a chance to some um, explore some state actions pairs that you normally wouldn't you wouldn't explore because the Q value is too high. Does that make sense? So we do the same thing again. We're going to generate episodes, right? We don't necessarily sample the initial condition now. We just say start from start from any spot. It doesn't matter, because on the next step, on the next step, I may not follow this policy, right? I may go off policy and do take a random action at that state. And that's going to allow me to explore the state space better than if I just tried to sample the state space at the initial condition. Right? So start from any spot. Doesn't really matter too much, although it doesn't matter too much where you start. But at each step in that episode, there's a chance that you're going to go off policy. And this actually turns out to be a really good way to sort of explore the state space more efficiently. Okay. But still, we have the same problem. One, you can't do this calculation. You need to generate an entire episode, whether you were following the policy or went off policy. You need to do it all first before you can start analyzing it. And still, what if the state space is huge, right? You're going to need many, many, many trajectories just to even sample it, even if you are exploring well. So these kinds of methods, both Monte Carlo and dynamic programming, when cast like this, don't really scale well when the state space starts blowing up. They both suffer from it. So we're going to need to think of a different way to treat that. Okay, but before we go on to continuous state spaces, I wanted to now introduce temporal difference learning, right? And you're going to see that temporal difference learning is going to combine the best of both worlds from dynamic programming and Monte Carlo. Okay, so like I said, so in dynamic programming, we need a model, right? We need a model, but we can evaluate on the fly. So at any given step, right? I'm at one state, because I have the probabilities, the transition probabilities to all other states. I can calculate the average right then and there at that state. I don't have to complete an entire episode. I don't need the environment to provide for me all the statistics. So I can do it one step at a time on the fly, but I need a model, of course. In Monte Carlo, you don't need a model. It's the opposite. You don't need a model, but you need to wait till you have a complete episode, right? So in temporal difference learning, combines the best of both worlds. So, and it looks like this. Temporal difference refers to just comparing the difference between one time step and the next. So I don't need to complete an entire episode. I'm gonna have the environment just generate me the next step, right? And that's what this is. So this looks almost exactly like we saw in dynamic programming, the update rule. This is just the Bellman, this is just like the Bellman all over again, right? Where the update to the new state is going to be the current value plus some time step. The reward realized in that state that you were, right? You took an action and you realized a reward plus some estimate of the discounted sum of future rewards, right? This is your estimate of the future rewards, right? It's what you actually realized, and plus some estimate of the rewards you can expect after that one step, right? And you're using your current estimate of the model. So it's bootstrapping, right? And that minus the estimate that you have for the current state, that's the difference, right? That's the error in it, right? So you're saying here, the value I assign to this state is X, and over here I have the estimated value for that state. That's going to be the immediate reward plus the future rewards, and when this equals that, learning stops. And so it's just like dynamic programming. There's a bootstrapping, but I don't need a model for it. I'm gonna use the environment like in Monte Carlo to generate for me the realized return, and I'm gonna use my current estimate of the state value to generate what the future rewards would be. Okay, so so this is how it looks algorithmically, right? So you need a policy though. We're going to start with a policy, and we say, you just write whatever step size you need. Okay, and we initialize the estimates for all the states to be arbitrary. We can say they're all 0, or we could assign them really high. It doesn't matter. We have some initial values for the estimates, and we're going to loop over episodes, right? So we initialize the state. We start from some state, and we're now going to march through that episode, right? So I begin in a current state, and my policy is going to tell me what action to take when I'm at that state. So that's A. Okay, and now I present these to the environment. All right, so I present the action to the environment, and the environment's going to give me the new state and the realized reward. And then I use that to update my estimate of the value. The value for that state is going to be R plus this discount factor of future rewards. So the rewards I could expect at that next state, right? Minus the value of this current state, and that's the error. So I update V of S this way, and then I overwrite. So now I'm in. I overwrite the state. So now I'm in now state S prime. I'm in S prime. My policy tells me to take a certain action. I take that action. The environment gives me a new state and reward, and I update again over and over and over and over until it converges. So this is how you do temporal difference learning when you have a policy, right? Remember, this is like the first step, right? You need a way to calculate the value before you can do policy improvement. Okay, so in temporal difference, a control in temporal difference learning is then going to be just following that policy, right? This isn't much different from what I showed earlier, right? What we're gonna do is you initialize S again, and then you choose an state action pair using the policy derived from Q, right? So for each state action pair, there's a value, and it can be greedy. It can be E-greedy. In other words, you pick the best one with some probability, and with some small probability, you can pick a random one, right? But nevertheless, you had a state action pair, and you use that, you plug it into the environment, that action, and it's going to update, it's going to give you a reward and then update the state, and then you use in order to estimate the future rewards, I need that new state and that new action, right? So I choose the new action from that new state given the policy that I have. I don't take it. I don't take that action. I just calculate what the new action would be in that new state, right? And you use that in the bootstrapping again to calculate what this future state is. So here is the value of the current state and action that I took. This is the realized return I got for taking that action at that state. And this is an estimate of the sum of future rewards if I started at that new state and I took that, and I took the appropriate action determined by my policy. And then you update your state and your action, and you loop over and over and over. So you need this tuple, this quadruple of data for each point. You need your state action at the current point, and you need your next state net action values to calculate this. This is known as SARSA learning, right? It's state, action, reward, future state, future action. You need all you need these elements to do this calculation, right? So SARSA is probably one of the more popular methods for doing TD control. Okay. And of course, this is telling you what your policy is going to be, right? Your policy then will be take the action that maximizes this value, right? You could do an off policy. Okay, yeah. Oh, so yeah. So the off policy version of TD control is the famous Q-learning algorithm, right? And what this one's going to do is now we're going to try to optimize the policy. Okay. So we initialize like before, right? Initialize by before, and we have a current policy pi, right? We start at some state S, and we're going to choose an action given that state using the policy that we have so far, okay? And we take an action and we present it to the environment, and the environment updates the state and gives us a reward, okay? And now we do this update rule not by the action that's dictated by our policy, but any action that give me the action that maximizes this value. So it could be off policy. Or it could be anything really, right? It's actually going to be policy, but since we're not taking the action A prime determined by this is why they call it off policy learning. And so now this is sometimes they call it SARS learning. There's no final A. So all you need is the state, the action you took, and the future state from the environment to do this algorithm. And this is actually pretty efficient, pretty fast. It's overcome a lot of the problems we've already talked about, right? You don't have to wait till the end of an episode. You're doing this on the fly, right? At every time step, you just present the environment with a state action pair, and it's going to give you the new state. You don't have to wait till the end of the episode. Yeah, you don't have to wait till the end of the episode, and you don't need a model, right? You're using the environment to give you what R and S prime are. Okay, so this is actually pretty old, right? It was introduced by Watkins in '89. But what makes it really cool now is that we can do offline learning here, right? And by offline learning, I mean, say that you had a data set already, right, of state action pairs, right? They weren't necessarily the policy that you're following now, but you have, you can use data from data in terms of episodes that were sampled by a policy that's not necessarily the policy that your policy that you're trying to optimize here. So that's actually really good that you can do. You don't have to do this on the fly. You could do some pre-training using the offline data to initialize your estimates of QSA. Okay, there is a big problem here though. Now these methods, when you're fully offline, off policy, tend to be a little unstable, right? And it comes from this bootstrapping. Oh, well, it comes from a lot of places, but one of the big places is this bootstrapping. So here is your current estimate. This is some model you have, right? It gives you a number. And here is itself, right? I'm calculating an error, and usually this would be like the ground truth, and this is your estimate, and you're improving on the ground truth. But this one's moving, and so is this one. They're both moving targets, and they may not converge when you're offline, off policy. They may not converge, And so, yeah, the algorithm can be unstable, right? And one way to get past this, to improve the stability, is what we call this double Q learning. And in that, you're going to have two independent models, right? One model we'll call the predictive model, and the other model we'll call like the target model. Okay, and every time you loop over this, you're going to switch which one's your target and um, which one's your target and which one's your predictor, right? So in one case, I update my predictor using the error between the predictor and the and the target model. Next time around, I switch which one's which, and now my target model is going to be updated using the value of the target model. But now, who's the ground truth has switched, right? You get what I'm saying? So doing it this way really improves the stability of the training. And there's a bunch of iterations. You can say like, learn. You don't have to do it every step. You could do like learn, update the predictor. I'll just call them model A and model B because they switch the target and predictor. But update model A 5 steps, and then switch to model B and update that one 5 steps, and then it doesn't have to be one to one. But usually, if you just switch every step, you get incredible improvement in the stability of the learning. So if you're going to do some Q learning like this, yeah, it's advised that you do some double learning. Have two models, and one learns off the other for stability. All right. Oh, this is double Q learning. So just like I said, so you have two models, Q1 and Q2, and in this case, they're doing it randomly. Every time you come into this loop, with a 50% chance, you're either updating one or updating the other. You can do it this way, or you can just say, every time, every loop around, I'm just going to switch one or the other. It's there's a bunch of ways you could do it. Okay, so that's double Q learning. So now actually I'm taking you all the way down to a stable version of Q learning that can handle off policy and offline learning, right? Which is pretty much everything you want, except for we're still in this case where the state space is discrete, right? We still have discrete states and discrete actions. And usually for real world problems, that's not the case. The state is some continuous thing. So we need to take this TD control and do it for continuous state spaces. All right. Oh yeah. So here's a quick recap because we're going to move on now. So dynamic programming, Monte Carlo, and temporal difference. Okay. So here, you can think of this kind of like the expense, right? How expensive the algorithm is. And in this way, this is kind of like for each time step, like how deep, how many steps in an episode do you need, right? So in Monte Carlo, you need the entire episode. You need the entire episode to make your estimate of Monte Carlo. With dynamic programming, you can go step by step on the fly, but you need statistics for all the transitions to all the states, right? So from one state, what is the probability of going to all the other states? So we say that's a wide update, right? That's going to scale by the number of states squared. So yeah, you only need to do it one time step, but you need to calculate for all the states. And in temporal difference learning, you take your current step and you only calculate for the action that optimizes that Q function, right? So it's only one-to-one. So it's really shallow, and it's a really shallow learning. It's inexpensive. And of course, on this end, you have just exhaustive search. I start in one state and I consider all possible actions, all possible states, average over everything, and then calculate every single path as it goes down. This is like ridiculous, right? All right. So temporal difference. So this is why temporal difference is so great, right? Because we're in this part of the graph. All right, so continuous state spaces. We have about 10 minutes left. So this is where I introduce neural networks, okay? So to treat a continuous state space, we're gonna need a function, right? We need that function that's going to assign a value to a state, right? And it's gonna assign a value to that state, and it's gonna be, you know, a model with parameters W, right? You could think of it as the weights in some deep network. But the point is, state goes in, and this is a continuous value, right? State goes in, this is just a function, and a scalar value for that state comes out. So, and this can be, it's not limited to neural networks. This can be, well, anything really that takes a continuous value here and returns a scalar for that value. Okay, but in neural networks, then you can optimize, learning then is just going to be a gradient method that's going to minimize the error of your predicted values versus your real values under some supervised learning scheme, right? And that's exactly, I'm going to backtrack a little bit for you guys. That's basically this, right? So this is the error, right? This is the target, this is the predicted value, and this is your target value, right? So so here, that's what this is saying. So the predicted value at your current state, given your weights, and minus some target value, right? If you bootstrap, you're using your own model to give you this value, but you have your targets and your predictions, and you calculate an error, and that's how you can update the weights by following the gradient. By following the gradient with respect to the weights, that'll tell you the forces on those weights. So this is just straight out of, this is just gradient descent, okay? So how to calculate this gradient here? All right. We'll do in a second. So in SARSA, semi-gradient descent just basically looks like this. So you start with a state and an action. You start in a state and you're going to get an action by, you know, it can maybe be some E-greedy method following some policy. And now you're going to loop over this episode, right? So you present that action to the environment, and it's going to give you the realized return and the future state. If that final state is terminal, then you can go ahead and update the weights. And how do you update it? So here's the error. This is the target term. Sorry. This is the error term, is the realized return minus your estimate of the state action with your model, times the gradient of that model with respect to W, right? So you update them. Yeah, and then your next action is going to be, you know, your updated model. Your updated model, and you use that to update the weights again. Here, this is your new target and prediction. I'm wondering why you're going over this next episode. This is technically then Monte Carlo, because you're taking the entire episode to update these weights. They're in the book, they have examples that's just SARS, not SARSA. And you wouldn't have this. But anyway, the update rules basically saying what we're doing is just, it's just supervised learning, right? You have your prediction, and your targets are, it's basically bootstrapped. It's going to be realized returns plus your estimate of the future rewards, and you do supervised learning like that following the gradient. So in neural networks, this gradient then is calculated in the usual way. So I have about 5 minutes to cover neural networks. Okay. I've covered this before in future talks. So I'll give you a link to the other talks too, but I'll quickly go through this example. Here we have a neural network of 3 layers. This is the input layer is linear, a hidden layer which is logistic nodes, and an output layer that is linear, right? So this is basically doing some regression. And these are the features X that go into it, right? So the values that these nodes take in this hidden layer is going to be the you're going to take a weighted sum of all the values in here. That's what this term Z is, right? It's you're you're taking those values in A in the layer below, weighting them by some weights. These are the parameters of the model. Add them all up, add a bias, and then stick that into a logistic function to give you the value of these nodes in each one. So because they're logistics, they're going to have a value between 0 and 1, 0 and 1. And this linear node is basically saying that. It's going to say, take a weighted average of these. So take the activity in the activity in the nodes in the layer below, weight them appropriately, add some bias if you want, and because it's a linear function, then that's it. And that's the activity of that node here. Right, so you can see how the data is fed forward, right? So the input goes into this linear layer. The states of these are fed into this logistic layer, and the states of these logistics are fed into this linear to finally give you an answer, a prediction y hat. We'll then use some loss function here to calculate the error. Here we'll just say it's mean squared error. Yeah. So here we have a mean squared error loss function, and we can now say, what is the derivative of this loss function with respect to the weights, right? That's what this is saying, right? So the derivative of the loss function with a particular weight in the layer below is going to be, well, it's just a realization of the chain rule, right? So y hat depends on the weights. Your prediction depends on the weights, right? Y doesn't, it's the ground truth. And so dl dw is going to be dl dA, right? A is the activity here. dA dz, z was the input to that layer, and then dz dw, right? It's just, that's how you get dl dw is just the chain rule like this. And you calculate each one of these terms, and I'm running out of time, but you can calculate each one of these terms, all right? So dl dA, well, the derivative of this with respect to A is just going to be the difference, right? The difference in the activity of the last layer here and the true value. That's exactly the term that appears here, right? It's going to be, this is the predicted value and this is the ground truth. Well, what stands for ground truth in this example, right? So that's this, DLDA is that one term. And this is the gradient of everything else, right? dA dz is just going to be the derivative of that activation function. And the z dw is going to be, well, you can, because z is just a linear combination of weights, it's just going to pull out that a term, right? This is always linear. Anyway, but the point is that this is the gradient bit that gets propagated down, right? And I've indicated here as dA. The derivative of a with respect to w is this bit. You pass that down to here, and you can calculate the derivatives with respect to the weights going down layer by layer by layer. This is just back propagation, and it's done through the realization of this chain rule, right? So now so given that you have all the delta W's, now you can calculate. That's exactly what this is saying here. This is the gradient of that loss function with respect to any weight in any layer. And that's what is asked here. The derivative of Q is your estimate, right? With respect to the weights. So to use a neural network, then you're just going to say Q, this Q function is no longer a function of discrete states and actions, but a function that takes in continuous states and continuous actions has certain parameters, and because it's continuous, you can calculate these derivatives to update it, right? So that's how it works. You substitute Q now for a neural network that takes in the state action in here and returns a scalar value, which you need to calculate this mean squared error. That was a very, very fast blur of neural networks. I will link you guys a deeper talk I gave on this whole, on this whole thing for your reference. But for next time, we're going to implement this, but you really don't need to do this because I've already coded up how to do neural networks, and I'll just show you how to use them, and you wouldn't have to worry about how it's calculated, how it's doing the back propagation, and how it's doing the gradient descent. It's just going to do it for you, right? And that's where we are. So we're now at the end here. Okay. So what I've done now is I've taken you all the way to off policy learning, right? I showed you how TD scales well. Was at that upper left-hand corner of that graph I showed you, right? It's shallow, and it's model free, so it's great, right? And I just showed you now how to use artificial neural networks to treat continuous state spaces. Okay. What's good about this is that you can now interpolate points between discrete states. If the state space was huge, it was hard to calculate the statistics, right? Remember? But ANNs get over that by treating the state space continuously. Okay, but next time we're gonna implement Q-learning for that snake game. Okay. So it'll be a little bit more hands-on. All right, guys. Do you have any questions so far? Yep. Yeah. So we are pretty much we finished all of part 1 of the book, and the material here is all the way up to maybe about halfway through part 2 of the book. So that's about 3/4 of the book all the way through. The last quarter of the book is actually just implementation. So we pretty much covered everything that's in the book. So I recommend that you guys go through it if you're at all interested in this. And next time we'll just walk you through this implementation, and hopefully we'll have a smart snake game. All right, guys, that's it. That's all I have for today. Okay.
Thank you, Dan.
Yeah, I'll